Hello, my name is Aarne Talman, and I'm presenting our paper NLI Data Sanity Check, assessing the effect of data corruption on model performance. This is joint work together with Maria Naapidianaki, Stergios Hatzikyriakidis, and Jörg Tiedemann. Let's start with natural language inference. So natural language inference, or NLI, is the task of, given two sentences, determine if there's an entailment relationship between the sentences, whether the sentences are in contradiction with each other, or whether the relationship is neutral. And there are some very popular NLI datasets, notably Stanford NLI, developed by Bauman and colleagues, multi-genre NLI, developed by Williams and colleagues, and adversarial NLI, developed by Nie and colleagues. And here you can see an example of an NLI sentence pair. You have the premise, a group of people are standing in front of a building, and a hypothesis, a group of people are in front of a building, and the task would be to determine whether there's an entailment relationship, whether these are in contradiction with each other, or whether there is no entailment or contradiction relationship, so they are neutral. So NLI benchmarks serve as test beds for measuring models' language understanding capabilities. This is based on the assumption that models should understand or at least somehow encode the meaning of the processed sentences in order to determine what the relationship between the sentences is. But is this really the case? There's been a lot of research and publications recently showing that there are annotation artifacts and statistical biases in these popular NLI datasets. For example, Polyak and colleagues and Gururangan and colleagues have shown that if you only take the hypothesis out of the two sentences, you can still get very high accuracy in these NLI tasks. There are results that show that contradictions are often marked with negation and entailments are marked with generic nouns. There are also specific words that appear in certain sentences. So for example, 90% of contradiction hypotheses in SNLI contain variants of sleep. And there's also lack of generalization across benchmarks. So we showed that if you train a model on Stanford NLI, for example, and then test that model with multi-NLI, accuracy gets very low. So this shows that rather than learning to do natural language inference in a general sense, the models learn specific factors of the dataset that they've been trained on. Very recently, Pham and colleagues have shown that you get high accuracy in NLI tasks after shuffling the word order in the sentences. So by shuffling the sentences, you break the grammatical structure of those sentences, but you still get high accuracy. So all of these results show that there are problems with these NLI datasets. But how do you determine if a NLI dataset is of high quality? How do you measure, how do you compare datasets with each other? So we took the approach that we systematically corrupt NLI sentences in NLI benchmarks by removing words of specific grammatical category, for example, words, nouns, adverbs, or adjectives, and create sentences that often do not make any sense. So for example, if you remove all the nouns from a sentence, these are often very difficult for humans to properly understand. And we use these corrupted data sets to test what is the impact on model performance. So for example, we assume that high model accuracy means that the data set is likely to contain statistical biases and other artifacts that guide prediction. Whereas large decrease in model accuracy would indicate that the original data set provides a proper challenge to model's reasoning capabilities. And on the right-hand side here, you can see a couple of examples from the MNLI dataset where nouns have been removed. They are here highlighted in red. And as you can see, some of these sentences without nouns would be very hard for even humans to categorize correctly. So let's look at the data sets that we created. For MNLI, we had 42 different configurations. We had 9 corruptions with specific word classes removed. These are listed here. We had 5 corruptions where only specific word classes were present and the other ones were removed. And we had 3 experimental setups per corruption. So we had corrupt train, where only the training set is corrupted. We have corrupt test, where only the test set is corrupted. And we have corrupt train and test, where both of these data sets are corrupted. For MNLI, we use the matched development set for testing, as annotated test sets are not publicly available. And we compare this with ANLI, and we create some comparison data sets, corrupted data sets from the original ANLI data set. So ANLI was specifically designed to address shortcomings of the previous NLI data sets. It contains 3 different rounds, round 1, 2, and 3, and each of these data sets were collected using human and model in the loop approach, and they progressively increase in difficulty and complexity. And here we have 24 different configurations. So we take all of the 3 rounds. We create 8 different configurations with specific word classes removed. And for ANLI, we only use the corrupt test experimental setup. This is because the training set in ANLI is very small, and training is done using combination of different NLI datasets. But also because we wanted to use ANLI more as a comparison dataset, we thought it doesn't make sense to reproduce all of the different experiments. We selected specific ones to test and compare against the MNLI results. The experimental setup for the MNLI tests, we used BERT Bayes model developed by Devlin and colleagues. We use the official training and evaluation scripts provided by Google with the default hyperparameter settings. And we measure the model's prediction accuracy in all of these 3 different configurations. So when the training set is corrupted, when the test set is corrupted, and when both the training and test sets are corrupted. And the results for MNLI are here. In the first column, you have the results for corrupt train, in the middle for corrupt test, and on the right-hand side for corrupt train and test. And the delta is the difference between the result as compared to the baseline result, which is 83.74%. And as you can see, in all of the different settings, MNLI with MNLI dataset, BERT achieves quite high accuracy, especially if you look at the 2 ones highlighted here, where verbs or nouns have been removed. The accuracy remains very high across all of the 3 different scenarios. And this indicates that there are some factors in the data set that guide the model prediction, as arguably when you remove all the nouns from the data, those sentences don't really make sense anymore. And the experimental setup for ANLI, we use Roberta Large model developed by Liu et al. We use the training and evaluation scripts provided by Nie and colleagues using the default hyperparameter values and other settings. And we measure the accuracy of the model on the 3 different rounds with different corruption settings. The reason why we chose Roberta model here instead of BERT is that we wanted to use the training and evaluation scripts provided by the authors of the paper in order to compare with their results as well. And here are the results for ANLI. So on the left-hand side column, you have the results for R1, in the middle for R2, and on the right-hand side for R3. And if you look at the 2 highlighted rows where verbs have been removed and where nouns have been removed, you can see that there's quite a large decrease in accuracy, especially with the R1 data set. For R2 and R3, these are lower, but this is because even the baselines are very low. So you can see the baselines at the bottom here. So as compared to the MNLI results, the decrease in accuracy, especially for when the nouns are removed and verbs are removed, is much higher. To summarize our findings, our results show a lower than expected decrease in performance for models fine-tuned or tested on corrupted data, where sentences are often unintelligible. Our results confirm that neural network models are able to solve NLI tasks by relying on statistical cues and artifacts in the data, and rather than understanding the meaning of the sentences, transformer-based models can leverage cues in the dataset to guide prediction. Our method also demonstrates the superior quality of the ANLI dataset, which was specifically designed to remove artifacts and biases from the data. To highlight areas of future research, we've listed specifically 3 areas. 1, our proposed methodology could be extended to other natural language understanding datasets and benchmarks. Our method can only indicate if a dataset is of high or low quality. It does not reveal the actual biases in the dataset. This should be analyzed in future research. Also, we think that there should be a comprehensive NLU dataset evaluation methodology and design guidelines to guide future dataset creation. Thank you for listening to our talk. If you have any questions, I'm happy to answer those. You can also contact me directly via email at the address shown here. Thank you.